All right. So last class period, we looked at the disk method of finding value. And so the basics of it is that we have some sort of an area and we're going to rotate that area around a vertical line or around a horizontal line to create a three-dimensional figure. And if we do that, we can find the value of the figure by thinking through cutting cross sections, and those cross sections that used to be our rectangles in the Riemann sum become disks when we rotate them around. All right. And we take the limit as the widths of the rectangles or the widths of the disks go to 0. And we end up with two volume formulas. And basically it's integrating pi r squared, where the radius is going to be different for different rectangles. So the radius here is a radius function rather than a standard single numerical value. So we're integrating essentially pi r squared, where r is our radius function. And if we rotated that around horizontally, then the disk's widths are all with respect to x. If we rotate that around a vertical axis of revolution, then our disk's widths are small changes in y's. So we have to integrate with respect to x when we have a horizontal axis of revolution, and with respect to y when we have a vertical axis of revolution. Okay. This is the one we did last time. We did example 1. So now let's move on to example 2. Find the volume of the object made by revolving the region created by y equals x squared, y equals 0, and x equals 2 around the x-axis. So the first thing I'm going to do is I'm going to look at the region. Y equals 2x squared is a parabola. Y equals 0 is the x-axis itself. And x equals 2 is a vertical line where all the x values are 2. And we're going to revolve that around the x-axis. Okay. So I just freehanded this. You could do it on your calculator. You could do it on Desmos. You could do it on whatever you want. But the only bounded region that shares those three as the exterior is this region in here. So let me shade that. I'll shade that in green. Okay, so that's my region. Now we're going to revolve it around the x-axis. If I want to make disks, I'm going to orient a rectangle like this. That might be hard to see. See if I do red better. So if I draw just some sort of a representative rectangle, the rectangle looks like that, right? And then I rotate it and I create a disk. Because this rectangle has width that is a small change in x, we're going to be integrating with respect to x. So our volume is going to be pi, integration from a to b, the radius function squared, all integrated with respect to x, and the radius function is done with respect to x. The nice thing about these, when I talk about the radius of a disk, and I rotated it around some line, the radius of the disk is always going to be from the top of the disk down to wherever I'm rotating around. Everybody understand that? The center of this disk is where I rotated around. So radius is going to be from the top of the disk to where I rotated around. Let me write that. Radius is from top of disk to the line we rotate around. So in this case, the top of my rectangle is the top of the disk that I'm going to draw, and in almost all cases. The line I rotate around is the y equals 0. So when I do this, my radius goes from 2x squared down to 0. And then I also have to figure out what the bounds are. Well, the bounds are going to be x values. And in this case, the x value of the left-hand side of my region is 0. The x value of the right-hand side of the region is 2. So my x values go from 0 to 2. At this stage, I can just plug that into my calculator. Again, I probably won't write the 0 when I type it into my calculator, but do be careful because we have something squared inside and then something squared on the outside too. So you have to be a little bit careful about that. I'm just going to type it in as it sits. So I'm going to type it in with the pi. And when I typed it in with the pi, I got 80.42 approximately. I said 80 and I wrote 80. 80.42. By the way, if you do that on your calculator, and then you divide this number by pi, not 80.42, but the number on your calculator by pi, that make sense, without rounding, you'll actually see this is like 25.6 times pi. Does this make sense? So we have some region, we create a three-dimensional object by rotating it around. I'm not drawing the three-dimensional object. Sometimes I'll draw that ghost image, but I didn't this time. Radius is always going to be from the top of the disk to the line you rotate around. All right, or the outside of the disk to the line you rotate around, depending on the scenario. Now, the natural question, so we've done two where we've rotated around the x-axis. Now let's rotate around the y-axis. Now, this is going to be the same region that we dealt with in example 1. Y equals 4 minus x squared. From, that's one of the outside edges. The other outside edge is x equals 0. That's our y-axis. And the other outside edge is y equals 0. That's our x-axis. And we're going to rotate that around the y-axis this time. All right, so we're looking at that first quadrant region. And we're going to rotate around the y-axis. In the disk method, if I rotate around a y-axis, the y-axis is a vertical axis of revolution. So I have to use y values. All right. Now I'm going to label the points on my graph. Where things intersect. Again, we've drawn this region before, last class period. So there it is. So we're looking at this region here, and we're revolving it around the y-axis. Because we revolve this around the y-axis, when I orient my rectangles, they're going to be this way, and therefore I have to use y values, and I get disks that are laying on their side, right? Stuff like that. So the volume is going to be pi times radius squared, but the radius is done with respect to y. In terms of the bounds are also done with respect to y. That's why they're called C and D. So we're going to go to the lowest y value in the region, that's y value 0, to the highest y value in the region, that's y value 4. So we're integrating from 0 to 4. Radius is still going to be outside edge of my disk to where I'm rotating it around. This one's nice because I'm rotating around 0. So it'll be something minus 0. But here's the trick. Normally we think of a function as function equal to expression in x, or y equal to expression in x. If I'm using y as my input variable, then I need to rewrite this as being solved with respect to x. So what I would do with my y equals 4 minus x squared, I guess I'll add x squared to both sides to get x on the left-hand side, and then I'll subtract y. Now, normally I can't just take the square root of both sides because I have to take the positive and the negative square root, right? But because this entire thing is in the first quadrant, I know that I can take the positive square root of both sides. Does that make sense? Since in first quadrant, so since it's in the first quadrant, the x and y's are all positive. So I can let x be equal to the positive square root of 4 minus y. Are you okay with that? So that's, I would have to be very careful if I did both quadrants. We wouldn't be rotating around y equals 0 though in that case. Or did I say that y, x equals 0, excuse me. Would not be rotating around the y-axis in that case. But since it's in the first quadrant, I can take the positive square root, and then I just plug that in. So the right-hand side of this radius of this rectangle is going to be the positive square root, and we're rotating it around the line x equals 0. So we do positive square root of 4 minus y down to 0. And then that's my radius, we're going to square. I keep drawing a rectangle just so we see the top and bottom. The line that I need to, or the curve, I should say. It gives me the outside bound and then where I'm rotating. Now, this is something you can put in your calculator. Although, you don't want to have a variable y in your calculator, right? Let me ask you this, don't write this down. What if you integrated this exact same thing, but you used a different letter? Let's say you use z. Would you have gotten the same thing? Yeah. And if you would have used some other variable, let's just say theta. Would you gotten the same thing? Sure, right? So no matter what variable you plug in, whether it's z, whether it's w, whether it's theta, whether it's y, or whether it's x, you'll get the exact same thing. And so when you write this in your calculator, just use the variable x for every time you see a y. Does that make sense? Or if you're in another mode, let's say you're in the polar mode, if you hit the variable key, it'll say theta. Or if you're in parametric mode, if you hit that variable key, it'll say t for parametric. Yeah.
How come you don't like using y on the calculator? Because I did it and just used things.
You use the letter y?
Yeah.
Oh, okay. Yeah, I always use the variable key, but if you use alpha y, you say you can do it if you use alpha y. Okay, yeah, if you use alpha y, that's fine too. Okay, but I'm so used to hitting the variable key that I just hit the variable key. Yeah.
I just want to make sure there wasn't like a reason to give you a different answer.
No, and that's exactly my point. No matter what variable you use, you'll get the same answer. So if you can do y on your calculator, go ahead and do y on your calculator. Let me actually type that in on my calculator. I'll do it both ways, just to show that it works. Okay. So here's my calculator. That was the last problem we did, integrating that one. So I'm gonna do pi and then integrate from 0 to 4. And then square root of 4 minus. Now again, if you just want to use the variable key, you just hit the variable key. And then hit the variable key again, right? So that's the way I did it. But if you want to use an actual y, it's alpha and then the number 1. So alpha and then the number 1. And then again, alpha, the number 1. Sure enough, you get the exact same thing. And if you're in a different mode, here I'm in the function mode. But let's say you were in the parametric mode. Oops. And you hit your variable button in the parametric mode variable, this classic variable is t in parametric mode. And so you hit your variable button, you get t. I know that's busy, but notice every time you get the same thing, no matter what letter you choose. So yeah, if you want to use alpha with the y, go ahead and do that. If you want to do just whatever variable key, if you're in function mode, your variable key is going to give you an x. If you're in parametric mode, your variable key is gonna give you a t. If you're in polar mode, your variable key is gonna give you a theta. All right. So no matter what you use, you get the exact same thing, which is just a fancy version of 8 pi. Right? So 8 pi is our final answer. And like I said, most times it'll ask you for the rounded version of that. Now I forget, 25.13. And you'd probably just write 25.13. So whichever way you write this, it's fine, whatever variable you choose to plug in. If you like to use the variable key, use the variable key. And if you like to use the variable key in parametric, use the variable key in parametric. If you like to use alpha y, use the actual y. If that makes your life, you know what I'm saying? If it's easier to understand that way, use that way. My whole point is it's just all giving you the same thing. Okay. Any questions about that? No. All right. Now, so far, we've revolved around either the x-axis or now the y-axis. So our radius was basically always the outside of the rectangle down to 0. Now let's take the region that's created by y equals 2 minus x squared and g of x equals 1. Rotated, so that region rotated around y equals 1. So the volume of that region rotated around y equals 1. Again, I tend to like drawing a picture. So I'm going to draw a picture, or I'm going to use my calculator to generate out the picture. One of the two. Let's draw it on the board. Y equals 2 minus x squared is a parabola pointed down. There's your y-axis, there's your x-axis. Now y equals 1 is a line that is horizontal and above the x-axis. That's this line, g of x equals 1. So these two things create the region. So the region is this region here. Okay. And we're rotating that around the line y equals 1, which is just that line in the region. Now, this is a horizontal line. So with the disk method, I am going to be using x values and my little rectangles are going to have widths of, with respect to x. Hard to see, but. Are you okay with that? Now, let's talk about these 2 points. This point over here and this point over here. This point, you can either look at this graphically and find the points, or you can set these two equal and solve, right? Whichever way you want to do it. So you can set this equal to that and solve, or you can do graphically. This point is -1, 1. This point is the point 1, 1. With that information, I can set up my integration. I know we're integrating with respect to x, pi r squared with respect to x. Remember, the radius is from top of the rectangle or outside edge. Let's say outside edge to line rotated around. So if the outside edge of my rectangle is determined by y equals 2 minus x squared, and the line that I'm rotating around is y equals 1, my radius becomes 2 minus x squared down to 1, that's just a -1. Does that make sense? 2 minus x squared down to 1, because 1 is the outside edge. The line I'm rotating around. My bounds are x values, so they go from -1 to 1. The x value bounds of the region. And then I can just type that into my calculator. And what I got as my final answer was approximately 3.35. It's like 16 over 15 times pi. Sixteen fifteenths pi, which is about 3.35.
Can you show your calculator on the screen by any chance, and see how you put it?
Yeah. I had my, so one thing I did is since these parentheses aren't doing anything, I didn't type those into my calculator. Just so I didn't have an extra set of parentheses. But, yeah, let me show you that. So I was still in parametric mode. But I typed it in as 2 minus t squared minus 1 in parentheses all squared. Again, I used the t because that was my variable key. And I just tend to use variable key each time, but if I'm a stickler about using x, could have done. Use x. Is that right?
Yeah, I did the same thing, and you got a different answer, and I don't know where I messed up.
Might look at your calculator because I wouldn't think.
I put a negative instead of a minus sign. There it is.
Oh, okay, yeah. Alright. Yeah.
Thank you.
Little, yeah, so that's the deal. Alright. So that's what happens when you revolve around a line that's not x equals 0 or y equals 0, right? You have to adjust your radius appropriately. Now, the next kind of curve that can come about is if my region does not touch or is not bounded along the line I'm rotating around. So far, in the first 4 examples, every time I had a region, that region shared a side with the line I rotated around. Right? So the side of the region was that. This one is different. This one I'm gonna have what I call space in between. Space in between my region and the line that's being rotated around. So we have y equals square root of x, y equals x squared, and we're revolving it around the x-axis. Now, you can graph this on your calculator. You can do whatever you want to figure out what the region looks like. But the region is this region in here. And we're revolving around the the x-axis, the x-axis. By the way, if you revolve this thing around the x-axis, think about what you could do. You put your hand in here, revolve it around, and it would never touch your hand, right? That's what we mean by space in between. So it's like a bowl, there's empty space in between there. This one would create an object that's kind of like a bowl, basically. What kind of objects are we getting? If I took a standard rectangle, and yes, because we're revolving around a horizontal line, it's going to be a rectangle done with respect to x. We're going to be integrating with respect to x, okay? Rectangles, width is a small change in x. If you revolve that around, you don't get a disk anymore. What you get is a disk with a hole in it. Does that make sense? So we get a disk with a hole in it. Which is just a washer, right? We get a lot of washers. And if you're trying to calculate the volume of a washer, what you do is you say, well, a washer is just a big disk with a smaller disk cut out of it. So, I didn't draw that very well. I draw it. That makes sense? So what we're gonna do is we're going to, when I have space in between, I'm gonna create basically two disk methods. And I'm gonna do disk method number 1 minus disk method number 2. All right? So when we have space, we have space in between the region and line rotated around. Then we use washers. and you do a disk method value minus a smaller disk method value. And the larger disk is coming from the outside edge, meaning the one that's further away from the line I'm rotating around. And the other, the one I'm subtracting, is going to be coming from the inside edge, the one that's closer than the line I'm rotating around. So in some sense, this red rectangle is like taking, a green rectangle, creating that disk, and then taking away, a black rectangle, that disk. Does that make sense? Very much like area in between curves, right? We're subtracting one from the other. When you go to set this up, the first disk method value, you usually use a capital R width. That's the outside edge. Then what do you think you'll use for the other disk method value? Lowercase r, exactly. Radius, big radius minus small radius, kind of thing. I have to erase this because I'm gonna write under here, but. So volume is gonna be equal big radius squared dx. Oh, forgot the pi out front. Small radius. All right. Remember, the radius is always the outside edge to the line we're rotating around. So the bigger one is going to go from square root of x down to 0. You okay with that? It's going to be here. And the smaller radius is going to go from x squared down to 0 in this region. Right, so bigger radius is this, from square root of x down to 0. Smaller radius inside edge is x squared down to 0. So that's how the volume is going to work out. Pi integrate square root of x down to 0. And the inside radius is going to be x squared down to 0. And when you integrate, the left-hand point is the origin. This right-hand point is the point 1, 1. So the x values are going from 0 to 1. And that's on both of those, right? That whole region. These, if we're talking about washer method, the A and the B will match up on both of these. Now, oftentimes, I just write that in one line on my calculator. So I write the whole thing in one line on my calculator. You can do two integrations on the same line, right? So that's what I tend to do. So let me do that. You just got to be very careful that you don't type in something incorrectly, obviously. Let me actually replace the spotlight, show that. So again, I've typed the whole thing on one line. Okay, see that? Hit enter, and I get about 0.94 as my final answer. Okay. I don't know what that is. So about 0.3 times pi. Or exactly 0.3 times pi. Okay. 0.3 times pi. If I type it in well, you can do it separately too. You can type in this integration first, this integration second, get answers, and then subtract. Another option, and this is the option that you'll see if you read along in the book. I don't like this one as much because it's more confusing than that I like to do it. I like to think of it as this method minus this method, all right? But the book will combine this into one integration. Because we have pi on the outside of both integrations, and because in both integrations we're integrating from 0 to 1, you could do square root of x minus 0 squared, and then minus x squared minus 0 squared, all integrated with respect to x. So you could combine it like that if you'd like to. And that's, again, if you read along in the book, that's how the book does it a lot. They'll use capital R squared minus lowercase r squared, all inside of the integration from a to b, all times pi. Any questions about that? And this is commonly referred to as the Washer method. The Washer method is just disk method minus another disk method. If we have space in between, we have to do disk minus disk. Okay. I want you to try to think through this one. I'll try to draw it on the board as we're working. But think through this one. This one's also, I believe, going to be the Washer method. So volume of a region, volume of the object created by revolving a certain region around the line y equals 4. That region is created by y equals 3 over 1 plus x, y equals 0, x equals 0, and x equals 3. revolved around the line y equals 4. This one's a little bit tricky, a little bit tricky. All right, let's talk about this one. Everybody see the region we're talking about? Could everybody graph that on their calculator and figure out what region we're talking about? And then we want to revolve it around y equals 4. Now, in this case, this is going to create a big, really huge loop going this way. So I could stick my whole arm through there and it would go around my arm just like a pipe, basically. Obviously, different thickness of the pipe, depending on where I'm at. So we're asking what's the volume of that thing? But there is a hole in there. I can stick my hand, I can stick my whole arm through that deal. So we're still using the washer method. We're going to use washers, which tells me I need to do disk method minus another disk method. Oh, and I should have drawn this, but I did not. A typical rectangle in the space, because we're rotating around a horizontal line, the rectangle is going to be oriented so that the width of the rectangle is some small change in x. So I am going to be integrating with respect to x. Now here's the tricky part. Remember, your radius always goes from the outside edge of the rectangle to the line you're rotating around. The outside edge this time is the y equals 0. Everybody follow that? Because that's the one that's further away from y equals 4. Now, here's a little nice thing about the disk method in general. We're going from 0 to 4. If somebody else would have actually said, well, actually, I think we should be going from 4 to 0, would they have gotten any different answer? No, because when we square this, if this were a -4 to begin with, squaring it would give me a positive 16. So if you do flip-flop your outside edge and the line you're rotating around, it's not going to hurt anything in the disk method. And technically, some people would say, hey, I think your radius should be positive. You should always call your radius positive. So some people would say, write your radius this way every time. That makes sense? But it doesn't matter if you flip-flop that. 4 to the outside edge of the rectangle, or outside edge of the rectangle to 4. So 0 to 4 or 4 to 0, either way is fine. Now we're going to go 4 to the inside edge of the rectangle. And the inside edge of the rectangle is 3 over 1 plus x. And again, if you want your radius to be positive, you write it this way. But if you do 3 over 1 plus x minus 4, that'll give you the same answer, because when we square any negatives, they'll become positive anyways. Now my x value bounds are the bounds of the region. And this region went from x of 0 to an x of 3. So we're integrating both of these from 0 to 3. Again, when I type these into my calculator, I'll put them on one line. Some people, when they type them into the calculator, would combine the integrations. And do something like that. Doesn't matter which way you type it in your calculator, just so long as you type it in correctly. Be very careful when you type in 3 divided by 1 plus x. Make sure the 1 plus x is all in the denominator. So let me do that. I haven't done that yet. I'll use that second version. That'll probably be quicker to type in my calculator. That way I don't have to do 2 integrations. 83.32 is my approximate value of that integral. By the way, that's not a very fun one to integrate by hand either, just so you know. It's doable. It's like partial fraction stuff. You get natural logs, and you get constants, you get natural logs. So you could do by hand if you really wanted to, using techniques that we dealt with in partial partial fractions. But, calculator is much easier to use, right? In approximate. Everybody get that? Figuring this out? So again, if we have holes in the middle, if we have open space in the middle, then we're dealing with washers. And then I have two radius. One of them is from the outside edge of the rectangle to the line I rotate around. One of them is from the inside edge of the rectangle to the line I rotate around. Okay. All right. I want you to try this one on your own. This one's one of the tougher ones. So y equals 5 minus x, y equals 0, y equals 4, and x equals 0 gives me the region I'm looking for. So we're going to have a bounded region. By the way, there's going to be two bounded regions when you draw this thing. It's the bounded region where the four sides enclose that region. And we're going to rotate around the line x equals 5. I want you to try this on your own. I'll give you some time to do that. Y equals 0, x equals 0, that's the x and y axis, so that's nice. Y equals 0 is the x axis. X equals 0 is the y axis. Y equals 4. Yeah,
Think so. Yeah, let's go to the this section, this section. So you carry it in this.
yes, that's it. Stack. So the second thing is, you gotta go from your line. Not down to zero, but the line, down to line and rotating. So the line, and then down up to 5, does that make sense?
So.
5 minus y minus 5, all inside
Yeah.
the squared, yeah. 5 minus y minus 5 inside the y, inside the squared.
What's the ratio? The down line,
No, it's the bottom one.
the bottom one, so this one right here.
Yes, yep, so that's the one that does the 4. Yeah. That's the one that shares all 4 sides. Does that make sense?
Yeah, if you have both sides, you might could show a little better.
Yeah.
It's definitely not. No.
Good. All right. Let me. Go through this. So it's similar to the last one. We did, in that there's gonna be space in between. But we're gonna be rotating around a vertical line rather than a horizontal one. So that's gonna throw a new wrench into what I'm doing. So when you draw these 4 curves, or these are all lines, so when you draw all 4 lines, you get this picture, and there's actually 2 bounded regions inside this picture. This bounded region, this little triangle, only touches 3 out of those 4 lines, right? So this little triangle only touches 3 out of the 4 lines. So the only region that touches all 4 lines that is bounded is this region here. So we're looking at that region. That I've shaded in green. Because we are revolving around a vertical line, x equals 5. Rectangles are going to be laid horizontally in the disk method. That means we're going to be integrating with respect to y. So everything I do integration wise is going to be with respect to y. I think which one I want to do first. Let me do this first. Okay, I know I'm going to be integrating with respect to y, so I'm going to change this up, this line here, and write x equals instead of y equals. And that's just going to cause me to add x and subtract y from both sides. And then I get x equals 5 minus y. Okay. The other lines that I'm dealing with are either x equals a number or y equals a number, so I'm fine with that. All right, so let's talk about the first radius. The first radius is gonna go from the outside of this rectangle to the line I'm rotating around. That's from x equals 0 to x equals 5. So you can either write 0 minus 5 or 5 minus 0. Doesn't matter because when we square it, if anything was negative, it'll become positive. What did I write? Yeah, I wrote 0 minus 5 when I typed it in. Then the inside of the rectangle to the line I'm rotating around is going to go from 5 minus y down to 5. So it's going to do 5 minus y down to 5. Oh, my integration obviously is with respect to y each time. Obviously, don't forget to square those radius. Don't forget to square each radius, I should say. Now, in terms of the bounds are y bounds. So what's the lowest y value? Clearly, the lowest y value is y equals 0. And then it goes up till you hit the highest y value. And the highest y value is y equals 4. So my integration is going to go from 0 to 4. Lots of different ways to type it into your calculator, but one of these two ways. Type it into your calculator. I used the second version and I got approximately 247.14, which when I divided by pi, I got 78 2/3 pi. As my exact answer. Anybody else get that? Same thing. So whenever we have space in between our region and the line I'm rotating around, I can do a washer method trick. Disk minus disk. Okay? Disk minus disk. Shouldn't say it's a trick. Washer method version. Disk minus disk. Now that concludes what I'm going to go through on 7.2. But I do want you to be very careful of something. All right? We haven't gone through one of these before yet. But let's pretend, I just want to make a note. If my region is something like this, so it goes from here to here, and then there's a straight line going from here to here. So if the region is going from, we'll say, A to B, and let's just, for the sake of argument, say we're going to rotate around the x-axis. but it's kind of like a piecewise defined function. All right? The rectangle tops in one section are going to be determined by this curve. But the rectangle tops in the other section are going to be determined by this curve, this line. Does that make sense? So if your rectangles in a certain part of your region are determined by one line, and rectangles in the other part of the region are determined by another, what you're gonna have to do is you're gonna have to split that region up into two pieces. Okay? So if the region looks like this, we need to split it up into two pieces. And calculate a value for both. We don't do that in this section very much, but. So if I have this big region, but it's determined by multiple curves, I might have to have multiple different values and add them up. Okay. So that might happen, that if our region is not a nice solid chunk, it looks like a few different things put together, then I might have to calculate a few different values and then add them all up. Again, we don't do that very much in this course, but you can imagine that happen. All right. So that's 7.2. Now, the interesting thing is that 7.3 also deals with value. Okay. But it uses another method. Let me motivate first, before we get into 7.3, let me motivate why you would want another method. I'm going to take a really, hopefully fairly easy region. All right. It's going to be created by y equals x to the third plus 2x plus 1 x equals 0, that's the y-axis. And y equals 5. And I'm gonna revolve it around the y-axis. Right? Now, I don't need to do a lot for this. Let's do Desmos real quick. YouTube up, get Desmos too. So y equals x to the third plus, what was it, 2x plus 1? There we go. X equals 0, y equals 5. Okay. So you can see the region that we're dealing with, it's right here. It's a nice solid, almost triangular piece region here, and we're going to revolve it around the y-axis. Now, really, the only thing that we need to do is realize that if we're revolving this around the y-axis, oh, I'm sorry, I didn't have that pulled down enough. So everybody see the region? Good. I didn't want to draw it on the board, so I figured might as well draw it in Desmos. Here's my region. If I'm revolving this around the y-axis, obviously, just going to be a solid value. The outside edge of a rectangle is going to go from this curve down to the line we're rotating around. Inside edge is the line we're rotating around, so don't need it. It's just a solid disk method. But the key thing is, because my rectangles in the disk method are oriented horizontally so that the width is done with respect to y, what I would have to do this would cause me to solve this equation for x and get an x equals something. And that causes me problems with this one, right? This one is not easy to solve for x. There is some nasty looking formulas and things like that with the third power, but imagine that is the fifth power, right? Wouldn't have changed anything other than the shape of the region. How would I have solved if that was x to the fifth plus 2x plus 1? Solve that for x. So that gives me a very big algebraic problem. okay? This is an algebraic problem. That would take me a long, long time to try to figure that out, longer than we have now. So instead of trying to use the disk method for everything, what we do is we transition to the idea of the shell method. Okay? And you can imagine what's going to happen with the shell method is that when we're revolving around a vertical line, like the y-axis, we'll be able to integrate with respect to x. And when we're revolving around a horizontal line, we'll be integrating with respect to y. Does that work? I don't know if we're either ahead of time or below time, I don't know. So here's what I'll do. I kind of want to start and do the shell method all next class period, okay? So instead of spending an extra 10 minutes trying to introduce the shell method today, what I think I'll do is I'll introduce the shell method next time. But again, the downfall of this method, you can see here that not everything is easy to solve for x. Not everything is easy to solve for y. So the shell method is a necessary thing. Another thing that also finds value, but a needed other method to find value. Okay? All right, so we'll start on the shell method next time. Any questions?